Thank you. So this is my first JPDK summit. So it's good to be here among all of you, among the community. Before being in the DPDK community, I have worked on a couple of networking applications using DPDK. So DPDK is not new to me, but I think developing features in DPDK for the applications is a different challenge. So today, what I wanted to talk about is the Q APIs. So my agenda is very simple. First, I'll talk about the motivation for these APIs. Then we'll yes. Then I'll talk about the Q API and the driver design. Then I'll go a little bit into the APIs. At this point, I have kept the APIs very simple, just to get a good feedback or initial feedback from the community. So coming to the motivation. Today morning we talked about the pipeline model of packet processing in DPDK. Just to be brief here, what happens in the pipeline model is you take the whole packet processing loop and cut that down into smaller chunks, and each chunk will run on one CPU core or one or multiple CPU cores. And then the core processes those packets and hands over those packets to the next stage or the next core in the pipeline. So here, for the inter-core communication, it uses the RTE ring, which is software implementation. Now, similarly, I saw that there are RTE event ring APIs. Those are again based on the software implementation. So these two are the primary mechanisms today in DPDK to exchange packets between two cores. So what happens with this is when you take this application and try to run it on a platform that supports hardware queues for inter-core communication, we still end up using the RTE ring. Instead of using the accelerated hardware rings, we still end up using the software implementation. So, what I feel is that we need to separate the ring or the queue implementation from the APIs. So that way we should be able to plug in a hardware ring implementation into those APIs. So this is the motivation or the thinking behind the Q APIs. So just coming to the design, there's already API and driver model well established in DPDK. I think we can follow the same model for the Q APIs as well. This allows us to separate out the APIs. The application will be written for these APIs, and then the implementations will plug into the driver. So like I have shown on the right side, you have got the application, then the APIs, and then you have got the driver framework. Driver framework is nothing but the ops structure. With the help of the driver framework, you can have multiple devices and the multiple drivers plugging into that framework. And that will allow the application to use the underlying implementation of the queue depending on what platform it's running on. So now coming to the how do we represent this device, the queue device? I think we can represent it as a queue manager, which to which you can request to allocate queues and free queues. And once the queues are allocated, you can use the NQ and DQ operations, that on those queues. So now with this, what we are going to have is we are going to have multiple implementations of the queue underneath, and I think that will present some challenges that I see. So the first challenge that I see is application portability. When you have multiple implementations of the queue, each one of them might have its own characteristics. For example, a hardware queue might be a non-blocking queue versus the RTE ring is not a non-blocking queue. But if we want to guarantee application portability between these two platforms, we need to make sure that application is aware of these differences in the characteristics. So that's one thought that I have considered in these APIs. The other thing that we need to take care is the APIs should address both software and hardware implementations. So with this, I would like to take a look at few basic APIs and some of the key data structures for those APIs. So obviously the first API would be the queue create API. So here, the first argument, the first thing is what do we return, what do we call, or what is the definition of RTE queue. So, I have made it as a union of private data and then an integer, basically. So I feel that in some of the hardwares, the queue is, it's just a 64-bit QID is nothing but a 64-bit integer. So, or it could be that you want to have your device and maintain some data along with it. So this structure would support both of them. And then the device itself is represented using the RTE queue context. So the first argument is the device. It's the white pointer, and it depends on your implementation or the underlying implementation. And then the queue operations, pointer to the queue operations for that device. So I think the other key thing here is the flags. So I think this is the key parameter that makes the applications portable across various platforms. So these flags should bring out different characteristics of the underlying implementation, so that the application is aware that there are these characteristics, and it can choose which characteristics it wants from the underlying algorithm. And I think that DPDK should make every effort to make sure all the underlying implementations provide the same characteristics where possible. But if not, these characteristics need to be brought up to the API level, so that application can decide for itself as to what characteristics it wants. So after that, Q3, very straightforward. So next, I have got the NQ burst. So one of the concerns I have is the passing this RTE queue context to all these APIs. I think I think that it can be the platform will have only one kind of queue device. So this is something that could be global. But at this point in the RFC, I have just kept it for each API, and we can decide whether that can be a global parameter or not. So one of the things that I have done is, I have tried to keep these APIs similar to the RTE ring and RTE event ring APIs, but I decided to take out the free space because I think that's something that cannot be that cannot be implemented by the hardware. But we'll see how the discussion goes, and we can change accordingly. So similarly for the DQ burst, I have taken out the available number of slots from the queue. So that's something again up discussion. Then I have got the RTQ get size. This will return the size of the object store or the memory that's occupied by that ring. And then I have the get capacity, which will give you the size of the queue, the usable size of the queue. So at this point, I have tried to keep it very simple, just to exchange the idea with the community. I have sent out the RFC yesterday. Feel free to provide your comments if you think it's good or bad, and we'll see how it goes. So that's it from my side. Any questions?
Any questions? 大家有问题吗？Thank you. Yeah. Oh, okay. We have questions. Sorry.
We know that there's an RT ring inside the DP already. So what's the difference and what's the improvement? And is there any hardware to improve performance?
Yes, I think so. So the hardware rings provide different characteristics than RTE ring. So RTE ring is a blocking algorithm, and some of the hardware ring implementations that I know are non-blocking. So non-blocking implementations are required in real-time threads, wherein your thread is supposed to get back to polling something in a fixed amount of time. So that we can't guarantee with the RTE ring. Yes, I think if having these APIs would allow us to plug in these hardware queues for